Okay, so today in this class, we are going to talk about what do we mean by systems on chip, how do we design them, how do we use them, and then we'll also talk about what FPGAs are, what are their purposes, how they're supposed to be used, and then we'll see how these two things can be combined to do some of the things that we will be doing in the practicals in this course. So without taking any more time, let's get into the content. So the first thing we're going to talk about is field programmable gate arrays, or FPGAs for short. I'm sure you guys are well familiar with what FPGAs are.
So FPGA is sort of like an integrated circuit that is designed to be, I could say, configured by the user.
That's quite a good answer. So it's something like an integrated circuit, which can be programmable or configurable by the users. So that actually summarizes it very well. So when we talk about hardware that are programmable, there are so many different levels. Even a computer processor, computer chip, is programmable at a very high level, right? A general purpose computer processor, CPU, is programmable at a very high level. You studied, know how this programming concept works for so many years. You know how that works. So FPGAs are also something like that, a piece of hardware that is programmable but at a different level. Then integrated circuits are typically, the typical traditional integrated circuits are not really programmable. You design them for a purpose and then that is it, right? Once you make the circuit, it will serve that one purpose. So your design is something, a logic circuit that you design with logic gates for a certain purpose. You have the inputs, you have the outputs, you have a function to be performed in the middle, and it goes through this process, right? You design, then you do something called synthesize, and then you go ahead and fabricate and package the chip, right? In this synthesis step, what happens is you are converting your register transfer level design or the gate level design into, in most cases, transistor level design. In usual cases, in an integrated circuit design, what you're ending up at the end of the day is with a silicon chip with transistors etched on it, right? Using the typical processing called lithography to dope the semiconductor with certain properties. So you have p-type and n-type and junctions, all kinds of junctions, and have the transistors and have them connected in the way you want. So that is what happens in the synthesis process. Convert your design into from a gate level design into a transistor level design. So that transistor level design, it is based on what sort of a chip you're expecting at the end. If it's an integrated circuit, it's usually a transistor level design that you're synthesizing into, right? So once the synthesis is complete, you will have your transistor level design. You can give that to a chip foundry where they will make a silicon chip based on that design, right? Put that design into silicon chip, a silicon wafer like this, right? Where a wafer can contain so many hundreds of copies of the same chip or different chips, and it will cost you an arm and a leg, to be honest, because it's going to cost, in dollar terms, several thousands of dollars to get a single chip made. If you want a single chip made, it's going to cost a lot. And then when you have the chip made, you put that chip into a package. The packaging provides insulation from electromagnetic activity and all sorts of interferences. as well as the packaging provides a means to put the chip into an overall circuit, into a circuit board, right? So you have different types of packaging. So this, the one on the picture is, it's called dual link line, where the pins are in two lines, and there are all sorts of other packaging, surface mounts, and so on, right? You guys are familiar with these terms, I hope. So you put the chip into packaging, and then you put that packaged chip onto a circuit board, right? That's how you use it. And once all this is done, the chip is going to perform whatever the function that it was designed to perform. And that's the only thing that chip can do. It can't do anything else, right? So that's how traditional integrated circuit design process work. Then compared to that, when you're working with FPGAs, you have a different process. You start from the other end. You start with an FPGA. You already buy a packaged chip, which has the chip, like Akhil said, but that chip is configurable, right? It's not designed for a single purpose. It's configurable to support different logic circuits. So you buy the chip, then you have your logic circuit design, the gate level design, and you have to synthesize it, not onto a transistor level design this time, because you're not going to take the design to a foundry and ask them to etch that on silicon, right? You are going to put that onto an FPGA, which is already there, wired, soldered onto a circuit board, packaged and soldered onto a circuit board. So you already have it. So you take your design, synthesize it on this onto whatever the primitive elements that the FPGA contains. FPGA contains a different type of elements, usually called as logic elements, and you are synthesizing your gate level design onto a logic elements design, and that can be put onto the FPGA. Or else we say the FPGA can be configured to support that design, to host that design, right? That is what we call or refer to as the programming of FPGAs. Yeah, we do call it programming, but it's not the same as programming as we usually know, right? Right? Computer software programs. It's not that. You make the circuit, synthesize it onto whatever the elements that are available on the FPGA, and then get the FPGA configured on that. So I hope the difference is clear. It's actually kind of straightforward, right? So the interesting thing, cool thing about this is, once you have the logic circuit on the FPGA, yeah, you can get the functionality from that logic circuit. But if you want some different functionality, you can come up with a different logic circuit, synthesize it again onto the same primitives, and then put that design onto the FPGA with same FPGA, right? The very exact same FPGA, and it will host that design. It will behave as that circuit, right? So that's the cool thing about the configurability or programmability at this level, right? It's kind of like you being able to write different software programs and run them on the same processor. But here we are working with digital logic circuits and being able to configure the hardware itself as that design, right? As that logic circuit. So, and you can go back and forth between all kinds of different logic circuits with the same FPGA. So it's a very flexible piece of hardware, and if you put an FPGA onto an end product, which you put out in the market, it allows you to say upgrade the hardware, the logic hardware later on, just like you provide software upgrades, right? You can have hardware upgrades where the circuit itself is upgraded, and then the FPGA is configured to hold that circuit. That flexibility allows a lot of new things to be done at industry level. So this is also the same concept or same process is also helpful for prototype. When you're designing a circuit and you're testing it at the very early stage of the design process, when you're working at the concept level, FPGAs are really great for prototyping, testing your design at the hardware level itself, right? So FPGAs are usually holding a place in between traditional integrated circuits and programmable computer processors, where the FPGAs allows certain degree of programmability at the logic circuits level, but it's also the circuit, the performance gained by the FPGA is not the same as if you made a dedicated integrated circuit, right? Because of the programmability, you are losing a certain amount of performance compared to integrated circuits, but you still have a lot better performance compared to programmable computer chips. Right? Okay. I hope the concepts are clear. Do you have any questions at this point? No? Okay. Just feel free to stop me at any time and ask questions, okay? Right. Now, if you take an FPGA and look inside what's there, you will see what you have inside there is something like this. You won't actually see, but yeah, this is something like this is what you will have. This is called as a reconfigurable logic fabric. So you have these logic elements or logic blocks. Different manufacturers call them by different names, logic blocks or logic elements. And they are connected by some sort of an internet. And it looks like a fabric, right? That's why it's called a logic fabric, right? It looks like a woven fabric. And then at these endpoints, you have input-output cells, which allows you to communicate with the outside world, outside the chip. So this is something like this is what you have inside an FPGA logic block, grid of a mesh of logic blocks connected by some sort of an internet. Then what do we have? Before we talk about what we have inside a logic block, yeah, you can configure these logic blocks or logic elements to represent different logic circuits, like I told you earlier, and provide that functionality, right? For example, if you want to make a computer processor, you can get the logic blocks to configure as a computer processor. On top of which, then you can run computer programs, right? Just like the processor that you build in your computer architecture course. If you synthesize that onto FPGA logic blocks, you can put it here. And that's the logic circuit that the FPGA will be hosting, right? So that's actually how this term field programmable comes, how the name is made. Because once you deploy a chip into the field, Even after that, you can program it. You can program it in the field. That is the sort of the meaning of this field programmable gate arrays. Right. So yeah, so this allows the logic block, the configuration of logic blocks allows us to host different circuits, complicated ones, simple ones, just like a processor can run multiple different programs. The FPGA can be configured to host multiple different logic circuits by combining these logic blocks in certain ways, right? So these logic blocks in the sort of the early days of the programmable logic hardware, they were simple gates, NAND gates or XOR gates, simple gates. They were a grid of simple gates, but now these days in modern FPGAs, we have complex units, these logic blocks. Sometimes they're called logic blocks or logic cells or LUTs, lookup tables. LUT stands for lookup tables, etc. Right? So a lot of different things. LUT is actually something that is inside a logic block. So just to give a very brief overview of these configurable logic blocks, they look something like this. You have an LUT or lookup table. Lookup table you can imagine as something like a truth table. So it can take a number of inputs. Depending on the manufacturer, they have different kinds of logic lookup tables. Number of inputs and an output, right? So, and there's a flip-flop to hold the state of the output and reset and clock signals to support this sequential logic, right? So that's it. That's what you have. So this lookup table is what gives you the configurability. You can, this lookup table, you can configure it to hold different truth tables. You can imagine it like the lookup table can hold different truth tables. It can be configured to work as with different truth tables. And that is how you can put different, say, configured FPGA to hold different logic circuits. Right? So this lookup table itself is configured. And if one lookup table is not enough to hold your design, you can use multiple configurable logic blocks, combine them, and get the functionality you want, right? So once your design is larger than a single lookup table or single configurable logic block, you have to route the logic blocks in an appropriate way to get your design, your large design onto the FPGA, right? Okay. So that's just some background about what FPGAs are and how they are used, how they are working. Then FPGAs, like I said, are used for different things, like being able to upgrade your hardware even after deploying, and being able to use FPGAs for prototyping, logic hardware design. And also FPGAs are used for performance, like I said. Now, FPGAs, even though they allow programmability like computer processors, since they don't have the burdening of computer software and all the intermediate things that will degrade performance, since the FPGA is actually closer to the integrated circuit level, the actual hardware level, digital electronics level, they are used for high performance applications. So improving performance of some application using FPGA can be done in one of two ways. One is this application specific hardware design. So in regular general purpose computer systems, you have your general purpose hardware, right? General purpose CPU with memory, input output, interconnects, buses, so, right? So you have the generic hardware to support application software. Then on top of this generic hardware, you have firmware or device drivers. Device drivers or firmware, what this device drivers allow is the functionality to interact with the hardware, because software is not directly allowed to manipulate hardware for security reasons, because you can't always trust application software. So operating system uses these firmware or device drivers to communicate with the hardware. So device drivers are the lowest levels of software that directly communicate with the hardware. Then operating system allows a lot of functionality like resource allocation, concurrent applications. Operating system provides a lot of functionality to the application level above it, right? So you're studying operating systems right now. So I hope you have some idea about the purpose of operating system. Then, yeah, and on top of that, you have application software or programs written to implement whatever the algorithm that the programmer wants. So the performance of the algorithm, the entire system, depends on all of these generic components, right? Generic hardware, firmware, and operating system. All of those components affect the performance of the system, even though the end user, what the end user or the programmer expect is the algorithm performance, it is affected by all of these different things, right? And operating system is using multiple different programs, and the time given for your program may be a very small amount compared to the overall system. So all kinds of these performance bottlenecks come into the picture. So compared to that, FPGA, the programmability of FPGA allows you to take your application algorithm and design the logic circuit based on that, right? Design an application-specific logic circuit based on your application and configure the logic fabric for that application, right? So what you will be having at the end of the day is a logic circuit itself, even though it is not at transistor level like integrated circuit. This is at logic elements or logic block level, but still you are getting much better performance compared to a general purpose programmable computer system. Is that idea clear? Yes or no? Come
Yes,
on, give some feedback. Yeah?
yes, sir.
Okay, right. So how FPGAs are used for improved performance is in one way through this application-specific hardware design. The other way is by exploiting parallelism. Now, FPGA, even though this particular image shows a very small mesh, you have thousands and even millions of these logic elements in a typical FPGA device. So you can host really large designs on a single FPGA. Now here, this yellow block is called IP because usually in hardware terms, a piece of hardware is called an intellectual property block, IP block. So this image, this FPGA fabric holds a small single IP block, right? So you can have multiple copies of that IP block if you want, or multiple copies different IP blocks as well. So if your application can be parallelized, then FPGAs will allow you to gain much better parallel performance compared to general purpose systems again, right? Because again, at the logic block level, you can get parallel functionality. So this is very similar to GPUs, the SIMD approach, single instruction, multiple data. If you have a small IP block, you can put an n number of the same IP block on the FPGA and get them to work in parallel on data. So this is somewhat like running, say, having multiple processor cores, but at a very different granularity, right? At a much lower level, you have hundreds of these IP blocks working in parallel on distributed data, right? So just like GPUs, you can get a lot of high performance through these parallelism in FPGAs. But the application has to support it, otherwise it doesn't make sense as always. So yeah, it can be identical circuits, multiple copies of identical circuits, or else it can be different circuits as well, heterogeneous designs as well, where you have multiple different IP blocks on the FPGA, and they will perform a lot of different tasks in parallel. So also, you can go for multiple FPGAs connected together to host massive designs. Even you can take a number of, say, large FPGA devices, connect them together, and get them to host a massive design. So this allows you to execute a lot of circuits, not execute also, host a lot of circuits in parallel on FPGA logic hardware. That is the second way that FPGAs are used to improve performance. Right. So this is just one example of a commercial use of FPGA for high performance applications. So I don't know whether you guys have heard about high frequency trading, or HFT. It's used in these what do you call it, stock markets and things like that, where people buy and sell stocks very quickly, right? Usually people analyze the data about the stocks, whether they are going up in value or going down in value, and make decisions to sell or buy at different points, right? So at this market, in these markets, this high frequency trading also happens, where people don't actually go and observe the changes in these values, but machines do. And usually FPGAs are now being used for this. So, so in markets like stocks, so forex markets, in places like that, FPGAs are used to analyze the market data really quickly and make decisions to buy or sell. So these buying and selling happens in sub-millisecond level. You buy and hold it only for a very short time, and then right, humans can't do it, machines can. So FPGAs are used to do this, and it's being actually used by a lot of companies to gain massive profits of by buying and selling stocks or forex or whatever the commodities. Yeah, so high frequency trading is one very popular application, and there are so many other applications like that. So in high frequency trading, so this is just one example. The financial institution is the market. The market provides the market data, and this here what's shown here is the FPGA unit. FPGA unit receives the market data through a very fast connection. It can handle a lot of data very quickly, and the overall management system runs on a traditional programmable computer, while the risk analysis and buying selling decisions are made at the FPGA level. So FPGA works with a computer processor to do the overall operation, but the high performance part happens on the FPGA. So that's just one example. And other examples include search engines like Microsoft Bing, and even Google uses FPGA for implementing their page ranking algorithms. That's again a place where you handle a lot of data very quickly. You need to handle a lot of data very quickly. Then these cloud services, distributed services like Microsoft Azure, to handle the host of services, the whole lot of services coming into their servers from all over the world, they use FPGAs again, right? So again, a parallel application. And then these hybrid computing is a sort of a new paradigm coming, emerging in the last couple of few years, where CPUs and FPGAs are used in parallel on the same chip. Right? Part of the chip is an FPGA, while the other part is a CPU. So again, these are targeting data center and cloud applications. So these hybrid processors are in the market now, and just to show the sort of the advent of FPGAs in the recent times, this Intel acquisition of Altera some years ago, I think about 5 years ago, this happened, 5 or 6 years ago. It happened for some $16.7 billion acquisition. It was a very big acquisition at the time. And Intel also plans to use FPGAs and build hybrid processors and server data center processors based on FPGA technology. So it's taking a lot of attention these days, but they're not new. FPGAs are not new. They are not some fancy new either. They've been around since 1980s, but they are making a comeback because the traditional CPU performance are reaching limits, coming against bottlenecks. So in order to support getting better performance out of these large-scale applications, FPGAs are again getting out of attention. All right, so that's it about FPGA. This is the FPGA board that you have borrowed, you will be using for the labs, and it contains a Cyclone 4 FPGA, Altera brand. Like I told you, Intel owns Altera. Now it goes as Intel Cyclone 4, I think. So yeah, so that is the FPGA. It's a decent sized FPGA, not a very big one. But this is an evaluation board intended for testing different things for educational purposes. So you have all sorts of different components on this board to be used with the FPGA. They are hardwired to different places, and you can check in the manual where each component is hardwired to, so you can connect from your FPGA device to that particular hardware, for example, USB, and be able to use that external hardware, right? So you have all kinds of different things, including these general purpose buttons, switches, bulb LEDs, up to a lot of communication devices like USB, Ethernet, and so on, right? Even VGA, all kinds of different things. So this is what we will be using in the labs, right? Then that's about FPGA, and I'll talk a little bit about systems on chip, right? So that's the other thing. So a system on chip, as we discussed on the very first day, it's a system on chip, basically, right? Where the entire system is on the same chip, including if you have a processor, if you have memory, if you have a timer, user device, whatever, right? Everything on the same chip. So then you guys have used microcontrollers in embedded systems course. Is that a SoC then? Does that count as a SoC? It's a bit of a gray area. Usually with microcontrollers, we don't consider them as SoCs. We consider as SoC a more slightly more performance-oriented device, where the processor is actually more capable of handling computations compared to a very small processor that you find in a microcontroller. Right, so microcontrollers are usually aimed at sensing and controlling the environment, right, for lower level embedded systems, whereas SoCs are aimed at handling more data with all the hardware on the same chip. So yeah, it's a microchip with all the necessary electronics and circuits on the same chip for a given system, right? It can have CPU, memory, cache if you need, DRAM controllers if you need, whatever, right? If you want GPU, it can be on the same chip, and all kinds of I/O hardware can be on the same chip depending on the application. Right? So, for example, if you're building a SoC for sound identification device like voice recognition or something like that, you will have a CPU or digital signal processor, DSP. You will have ADC, probably multiple ADCs. You will have memory on the same chip, and you will have a lot of other I/O units on the same chip, right? So depending on the application, all the required hardware is on the same chip. The idea is you don't have to spend a lot of time or power to communicate between these elements. Otherwise, if you have different elements and different chips and they are connected through a circuit board, you are wasting, not that you're wasting, but you're spending a lot of power as well as time in order to get the entire thing to collaborate and work. Right? So that is where the power of systems on chip comes into it. Right. So yeah, benefits benefits are increased performance because of low communication delays, low power consumption, again because of very short distance communication, and of course smaller size and smaller size of the chip as well as the product that you're making, the device that you're making, which also results in reduced overall cost. So now we'll see a bit about these two ideas combined, right? Systems on chip and FPGA. What happens when we combine these two ideas and try to build a system with both concepts? So in FPGA gives the reconfigurable logic fabric, and the SoC components, CPU, memory, and whatnot, can be put onto the FPGA, right? So the CPU allows you to run software programs on it, and the FPGA still allows the flexibility, configurability to have different elements along with the processor to act as a SoC, act as a system on chip. Still giving you that flexibility to prototype, flexibility to upgrade, and all sorts of additional benefits coming with FPGA. Right. Okay. So in this context, how does the complete system look like? Now, earlier we had generic computer hardware with device drivers, operating system, and application software, right? So how, when these things are combined, how do they look like? So at the top, you have application software, as usual, algorithms converted into software programs. Then after that, you have you usually have operating system. This is dependent on the system that you're building. You might or might not have an operating system, or sometimes a real-time operating system if you need real-time guarantees from this system, embedded system that you're building. The operating system will have the protocols to support, say, provide different functionality to software. It will provide security between different applications and between using hardware. Then it will support abstract concepts like file systems and so on, right? You will learn these things in operating systems. So all those things are provided by operating system. Then underneath that, you have this firmware layer, which we refer to in FPGA context as HAL, or hardware abstraction layer, right? Essentially, it's a collection of device drivers. But the thing is, the devices in hardware are not fixed, right? You, as the designer, design the hardware that you put onto the FPGA fabric. So the device drivers also have to be built or generated for those hardware components, right? So you have the hardware abstraction layer, which is also tied to the different configurable hardware that you have in the lower level. So in the lower level, you have the SoC hardware components, CPU, memory, cache, ADC, counters, whatnot, right? All the components of your SoC. And that is hosted by the FPGA, the logic fabric, right? So logic fabric itself is configured to act as the system on chip. And on top of that, you have the hardware abstraction layer containing device drivers for all the different elements. And then the operating system provides the abstractions from the hardware abstraction layer to the application software. So that is how an overall system looks like in this context of FPGAs hosting systems on chip. Right. So design steps go like this. First, you design the system on chip with the different components you want in it, CPU, memory, whatnot. You can do this design using a hardware description language like Verilog or VHDL, or else you can use block diagrams or schematic diagrams or state machines. You can use different methods to model and design the system on chip. You have learned some of these earlier. You will learn some more in this course, in the theory classes. So yeah, so designing the SoC is the first thing. Then you do something called analysis and elaboration, where you check your design for errors, syntax errors and semantic errors, right? You check your design whether it contains all these different errors that are identifiable by the compiler level, right? So this is part of the operation of the compiler, analysis and elaboration. Then once that is done, you do something called pin planning. That is mapping the input-output connections of your system on chip to actual physical pins of the FPGA. Right? FPGA connects a number of pins, and those allow the communication from the FPGA, whatever inside the FPGA, to the outside world. Right? So pin planning is where you do this mapping. The inputs and outputs of your SoC, how do you map them to the pins, the physical pins of the FPGA device? That's number 3. Then once that is done, you go on to the next part of the compilation. Actually, all of the things that I mentioned earlier, number 2 and 3, are also parts of the overall compilation process. Here we do the next part is mainly synthesis, right? Technology mapping from the gate level design to the configurable logic block level. And once that is done, optimize the usage of logic blocks by combining, distributing the design over the available logic blocks in an optimal way. then route the logic blocks, connect the logic blocks in an appropriate way to get the entire design to work as you specify. And once that is done, most of the hardware stuff are done. Then the next step is generating an assembler, right? You have a system on chip containing a CPU, a soft processor, right? Then in order to run programs on that processor, you need an assembler. So you can write assembly programs and run them on the processor, or else even convert from a higher level language like C into assembly and then into machine code, right? So that assembler is dependent on the CPU, right? It depends on the CPU, instruction set architecture and whatnot. So that assembler has to be generated because you can configure the CPU of the SoC to do various different things, right? Because these are application specific designs we're talking about. So CPU itself can be customized. So the assembler has to be generated at compile time. So you can write programs for your SoC. Okay, and once that is done, you do something called timing analysis to make sure that your hardware design meets the timing requirement. If you have a timing requirement, to make sure that the hardware design meets that. So for example, that is where the maximum clock is decided. What is the maximum clock frequency that you can use for this particular system on chip on FPGA, right? Okay. But once that is done, you can download your design onto the FPGA, or we can do the so-called programming of FPGA. Right? Download the compile design onto the FPGA, configure the logic fabric in that way, and the FPGA will behave as a logic circuit. Right. So that's the hardware side of things. Then from the software side of your system, you need to generate the hardware abstraction layer. So that is this low-level code to support software, including device drivers, right? So you also need to define things like memory layout. If you have memory in your SoC, how the memory is structured, which address space ranges are accessible by which CPUs if you have multiple CPUs, so which applications if you have multiple applications, and so on, and then generate compile support for application software, right? You generate the assembler earlier, and at this hardware abstraction layer level, you will generate the compile support for application software. Okay. Then operating system, if you need an operating system, you can have. So you have these embedded operating systems like Micro C OS2 or even Linux, different versions of Linux. You can have as your operating system. And again, this all depends on your requirement, whether or not you need an operating system for your embedded system. If you need, if you need advanced resource management and security or support for file systems, you might need an operating system. And then you build software programs, and you write programs in C or assembly and download them onto the system on chip that is now on your FPGA. And the functionality of using hardware from your application is implemented through this hardware abstraction layer. Right. Once the software is ready, you can launch them onto the FPGA and get them running. Okay, so that is the process that we follow, design process that we follow when we are working with systems on chip on FPGA. Now, in the lab, you guys have already started, but we'll be doing in this first practical is building and testing a system on chip on FPGA. There are two parts. First one is actually a walkthrough where you get familiar with the tools. The second one is where you implement a system on chip to perform JPG encoding on FPGA. Right. So yeah, the learning objectives are to get familiarized with the concepts design a synthesis of system-on-chip hardware using FPGA tools, the core design of hardware and software. As you can see, in these higher level embedded systems or advanced embedded systems, we have a significant software component, and we design the software component and hardware component together because they are very much interconnected, right? They are tightly coupled in other words. Right. So the tools you already know, Altera Quartus version 12.1 or 13.1. These are all versions, but these will definitely support. I have tested all the designs on this, but the later versions also should support, I think, without much issues. I hope you guys all managed to install the software and you all already have the FPGA board. So that's good. So yeah, part one, getting started. This is a very simple step-by-step guide. This is what you have on the on your SoC system with the CPU, memory on the chip, and some general purpose input outputs, UART, and some other elements, right? Then in part two, you have a slightly more complicated system, a SoC to encode JPEG. And for this, you use the onboard memory chip that you have, right? You can have memory on the chip as well, but just to get you exposed onto these other technologies, we are using the onboard DRAM chip. So this is on the board, on the evaluation board, not on the FPGA chip. So in order to access the onboard DRAM chip, you need to have the DRAM controller on the FPGA chip. DRAM controller is what the protocol interface between your CPU and the actual DRAM memory bank. So the other elements are pretty much similar other than this clock crossing, which again, that is to get you familiarized with different techniques. So on the FPGA, you have two different clock domains. One is the 100 MHz clock domain, and the other one is the 10 MHz clock domain. So in order for you to communicate between these different clock domains, the elements hardware in different clock domains, you need a clock crossing bridge. The CPU operates at 100 MHz. The timer and system ID operates at 10 MHz. So for the CPU to communicate with the timer, you need the clock crossing bridge. And also we have a PLL this time, which PLL is phase lock loop to generate different clocks. Why? Because we have these two different clock domains. Yeah, one reason. The other is to implement the communication between the on-chip CPU and the off-chip memory, right? So when you try to communicate between these two, you have to synchronize the communication, right? These are synchronized with a clock. If you use the very same clock signal for the on-chip components as well as the off-chip memory, you encounter something called clock skew. Clock skew is the clock, the rising edges and the falling edges of clock being slowed down when it is transmitted through a very long copper wire to an off-chip component, right? So what happens is the rising edge that the CPU experiences and the rising edge that the same rising edge that the onboard on-chip off-chip RAM experiences happen at two different times, right? Because the signal gets delayed through the copper connection. That is clock skew, right? The timing becomes different. The same clock edge is occurring at a delayed time for the off-chip device. So in order to counter that, what we do is we come up with a clock with the same frequency, but negative phase shifted to the left, right? Negative phase shifted. So we provide the negative phase shifted clock to the onboard, the off-chip memory, while we provide the regular clock with the same frequency to CPU. So the idea is to have the delayed clock edge for the off-chip device and the regular clock edge for the on-chip device synchronized to the exact same time, so the communication can happen between them. So in order to do that, we need to know the actual timing delays that the copper wires on the board that you're using is experiencing, right? So those are already measured and the values are provided. So we can use the negative phase shift as given in the lab document to implement the off-chip communication.